Gaitsgory from Harvard University, who will speak on the Tamagawa number formula via Chiral Homology.
Thank you very much. So hopefully what I'll talk about today will be written down soon. Jacob is in the process. So we start with K. It's a global field of characteristic P. And so if you take Y as any smooth algebraic variety over K, if you pick so a top degree differential form on Y, if you pick a measure on adels on K, that produces a measure on the adelic points of Y. And so the main observation is that so this resulting measure is well defined, is independent of the choices. So we are going to take Y to be an algebraic group. And so if the group is semi-simple, the total volume of, let's call it Tamagawa measure of the adelic quotient is finite. So for this talk, I will concentrate on the case when G is just a constant group scheme. I mean, so we have our curve over function over the ground field FQ, and we assume that G is just pulled back from a group scheme, algebraic group over FQ. So now, the Tamagawa number formula says that when G is simply connected, this total measure is equal to 1. So let me reformulate what this means, well, in kind of very concrete terms, in my case of a constant group scheme. So, well, then so the main observation is, of course, that in this case, if you consider this quotient and you mod out by integral adels, this is the set of FQ points of this gadget, which is the moduli space of principal G bundles on the curve. Now, what you want to do, so this being, well, it's not exactly a set. It's set, but each point has a finite group of automorphisms. So therefore, it also comes with a natural atomic measure, and you want to compare the two. So this theorem is equivalent to, well, the following calculation. So the number of points, but of course the set is infinite, and so the reason that this number is well defined is one has convergence, which again it's due to the presence of automorphism of points. So it's given by the following formula. So let me write it down. It's Q inverse to the power the dimension of G times G minus 1, where G is the genus of the curve. Well, times, well, this is kind of boring factor, times the interesting factor, which is the following. It's the product over all closed points of the curve, and it's the product over the set that I call, well, it's called the exponents of the group. I'll remind you what they are in a second. And then we take 1 over 1 minus Qx is, well, the number of elements in the residue field at the point x to the power minus E alpha. So, well, these are the labels for the exponents. These are the exponents themselves. So let me remind you what the exponents are. Well, the definition that kind of, well, but we'll be using all the time is the following. Let's consider the classifying space of the group and to consider its cohomology. So, well, otherwise known as the equivariant cohomology of the point with respect to our group. And so this is a symmetric algebra on a certain vector space. Well, let me call this vector space alpha. This kind of A and A. If you take into account the action of the Frobenius, it looks as follows. It's direct sum of exactly these exponents here of, well, QL of minus E alpha For example, if your group is SL2, all I'm saying is that the equivariant cohomology is the symmetric algebra in one generator which sits in cohomological degree 4 and has weight 2. Yes.
And this computation, do you use as a principle for it?
Well, yes. What you need to know is that every G bundle splits.
Yes.
Yeah. All right. So that's what we want to compute. So what we want to do, let's try to consider cohomology with compact supports of this BunG. So first of all, what is it? So BunG is not quasi-compact. So this is defined as the direct limit of over quasi-compact open substacks. Well, there's a filtered family of those that exhaust BunG, and we take cohomology of with compact support each of these guys. So here comes the following observation, and you may try to look how Frobenius acts on this vector space. This is an infinite dimensional vector space. So first of all, generalized eigenspaces are finite dimensional. Second, so you can try to take the trace of the Frobenius on each of these generalized eigenspaces. So you'll be getting, well, algebraic numbers. So the claim is that, well, so you'll have absolute convergence. When you sum over different eigenvalues, it'll be absolutely convergent series. So trace of the Frobenius on this cohomology, and this is a property. It won't be true for some arbitrary non-quasi-compact algebraic stack. That's a property of BunG. So you have to know something about it, and what you actually know is that it has a very explicit stratification which you can control. It's this by the type of the Hardener Simon flag. So is absolutely convergent. And moreover, so this trace of the Frobenius equals this number of points. Again, so what you do, you consider this nice open subsets which you can control. This identity holds over each of them, and then you see that both sums absolutely converge. By using that.
Algebraic stack with finite automorphism group, this kind of formula would not be true.
Just one second. So
I will stop, sorry. And this cohomology is compact support that's defined by duality?
well, I've been. You mean from cohomology? You mean that's one way, but it's well, we'll get back to it. I mean, it's better behaved as this. So That's my next remark. So now so what I want to do first, I want to get rid of this boring factor. So let's define homology. Well, now this is for an arbitrary algebraic stack as cohomology with compact support, but with coefficients in the dualizing complex. And so, well, if your algebraic stack is smooth, the dualizing complex is the just shifted constant sheaf. And so, well, that picks up exactly this number. So what you actually want to show, so what we, because of this lemma, want to compute the trace of the Frobenius on the homology of BunG. And what we want to show that it's equal to this product. So basically what you want to do, you want to understand this vector space as acted on by the Frobenius. So now let me give you the answer. So I'm reformulating what I want to prove in terms of the following theorem, that BunG as a vector space with an action of the Frobenius is the following. It's the symmetric algebra on, well, the following. You take the cohomology of your curve tensored with the vector space dual to this creature alpha that I introduced up there. Dually, well, this is equivalent to the following. It's the cohomology of BunG. So, well, usually homology is some in the vector space. Cohomology is its dual, it's pro. So in this sense, this is better behaved. And again, I'll get back to this point in a moment. This is sim, but, well, in the completed sense of now we take A without dualization, but here we're taking the homology of our curve. Now, if you look at this formula, you'll recognize that this is exactly the Atiyah-Bott formula for the cohomology of BunG. So in their 1980 paper, so they gave this. So I can tell you, well, of course, they stated it for BunG for curves over complex numbers. And so the idea of their proof is that you can uniformize this moduli space, well, in differential geometry using connections on the trivial bundle. And that's how you control the topology. So basically what our work with Jacob amounts to is just giving an algebraic proof of the Atiyah-Bott formula. And so that's what I'm going to do. Yes, and well, it's easy to see. It's a standard trick to see that the trace of the Frobenius on this is exactly this. So it's kind of easy calculation. All right, so now let me go a little bit into the machinery. So to prove this kind of thing, we will have to leave the world of algebraic varieties and we have to leave the world of algebraic stacks. So what we're going to do, we're going to consider this very general object called pre-stacks. So pre-stack is an arbitrary functor from contravariant functor from the category of affine schemes of finite type. Well, I'll write set to the category of sets, but in fact, that won't do. In fact, you have to replace it by infinity groupoids. So you have to, well, even usual stacks, they are not sets. The points have automorphisms. In general, you have to consider automorphisms, automorphisms of automorphisms, and so on. So you are in the world of homotopy theory. So I'll right away give you an example of such. Well, one example is, of course, schemes. Another example is BunG, which is one stack, but the object that will appear prominently is the run space of my curve. Well, I'll suppress the curve, and that's the following thing. It's so hom from S to the round space, well, this will happen to be a set. It's not infinity groupoid. Is the following thing. It's the set of all finite subsets, all non-empty finite subsets inside hom from S to X. And this creature is very, very far from being an algebraic variety. It's not even in the scheme. It's horrible from some point of view. From the other point of view, we'll be able to work with it. All right. So what are we going to do with pre-stacks? So first of all, here's the piece of math that hasn't been fully documented in this context. So there is a functor from the category, again, opposite of affine schemes, to, well, one should say that stable infinity categories. And the functor is called the derived category of laddic sheaves with constructible cohomology. So, well, I'll write it. So y goes to db const y, QL coefficients. So this is a small category, and one has to appropriately complete it, one to allow formal inductive limits. So, well, what we know is that one can produce the corresponding triangulated category. So what has not been documented, that it's in fact can be upgraded to this more rigid homotopy level, and that's necessary if, well, for the kinds of operation that I'm going to perform. So basically what happens is that if you're working with triangulated categories, you cannot form limits, but this is possible in this appropriate homotopy framework. And so I'll tell you exactly in a moment what kind of limits do I need to form. So UNEDO embedding embeds affine schemes into pre-stacks. And the claim is that there is an automatic procedure of extending this functor to pre-stacks. Well, topologists call such procedure right Kahn extension. So let me tell you what I mean. So I have to tell you what is an laddic sheaf on an arbitrary pre-stack. So by definition, so an laddic sheaf, let me call it D, we call this category D, on an arbitrary pre-stack Y is the following collection. Is for every scheme S equipped with which maps to Y, we prescribe, call it little y, Fs, which is an laddic sheaf on S. Yeah. Object of that. Well, this is informal, yeah. Kind of technically, one forms a limit. Intuitively, what an object of this limit is assignment, again, for every affine scheme mapping to Y of an object. If you have S1 mapping to S2, well, this is Y1, this is Y2. Well, now, because in general Y doesn't take values in sets, a datum of commutativity, it's not a property, it's a datum. So you have to make this commute. So for every triangle like this, so let's call this map little f, you prescribe. So on the one hand, we have f sub S2 that lives on S2. On the other hand, we have lives on S1. Now, so what we have to do, we have to identify the pullback of the guy that lives on S2 with the guy that lives on S1. Now, which pullback? Well, there is a choice in the theory, and for my purposes, the pullback that will be convenient is this choice. It's the Schrieg pullback. And of course, because you're in this higher homotopy world, when you're saying this, you have to do it not only for just compositions, but two-fold compositions, in fact, all n-fold compositions. it's the same. So now the formalism is such that, well, what you can do always, if you have a map of pre-stacks, call it F, you automatically have a pullback functor in this direction. You don't have much else. You have functoriality like so. However, that gives you, well, you may or may not be able to define F lower shriek. So namely, if you have any functor, it always has a partially defined left adjoint. Just consider those objects, well, for which you can define left adjoint. So if your functor, if your map is such that the left adjoint is defined on all objects, well, so lucky we are. Now, in particular, any pre-stack maps to the point. And we define the dualizing sheaf as just this upper shriek of, well, the constant sheaf on the point. Now, you can define the homology of a pre-stack, if it exists, to be, well, F lower shriek, the dualizing, where F is the map from Y to the point. But the claim is that this dualizing is an object on which this functor is always defined. So homology is well defined for an arbitrary pre-stack. Now, just because I may forget later, let me just say that for certain pre-stacks, you can guarantee that this functor for the projection to the point is always defined. And the run space will be such because our curve is projective. All right, so now let me introduce kind of the main player in this game. This is a factorization algebra. So definition, a factorization algebra A on X is the following datum, is a datum of an object that I call A in this category on the run space. So considering run space as a pre-sheaf, well, equipped with the datum of factorization, and that is the following. So there is an evident map from the run space times the run space to itself. Namely, it's the union of finite sets. So again, a map from a test scheme to the run space is a finite set inside hom from this test scheme to X. We take the union. And inside, there is an open subfunctor corresponding to the condition that so our two finite subsets have non-intersecting graphs. So let's call this map addition. So the datum of factorization is the following. We pull back our A by means of this map. Well, let me call it maybe this map addition. And then restrict to this open subset, well, open subfunctor. And when I say restricted, again, it's the same upper shriek pullback functor on the one hand. On the other hand, you can take, well, the exterior product, which lives here, and again restrict. And the datum factorization is an isomorphism. Again, if we were living in some sort of abelian category, that would be the only data required, and one would have to require the condition of associativity. In the higher homotopy world, you have to prescribe it, well, not for the just twofold product, by all n-fold products in a homotopy coherent way. So this is a datum of factorization algebra, and we'll see a bunch today. let me just say that if you are over C and you replace the world of L-adic sheaves by D-modules, this is equivalent to the notion of chiral algebra that appears in the book of Bellingson and Drinfeld. Pardon me? Yes, so it's extendable from schemes, from affine schemes.
Was there a reason to first is add a Bufrik and then restrict, or take just an Bufrik for decomposition?
It's the same. I just wrote it for symmetry reasons. So, why am I saying all this? It's because I want to reinterpret in this form the Atiyah-Bott formula. So, one of the observations is that if A is just commutative algebra over QL, you can create A, which is a factorization algebra on X. So let me say what it is. Let me say what its Schrieg fibers are at points of the Rand space. So if you have an actually, well, field-valued points of the Rand space, let's say FQ-valued points. So we have just a finite collection, finite subset of points in your curve. The Schrieg fiber of A at this point of the Rand space is just, well, the tensor product of that many copies of A. Well, in fact, I should have broken this procedure in two steps. I could have started with just not a commutative algebra of the point. I could have started with a commutative algebra inside the category of L-adic sheaves on the curve, in which case I would be taking x1, x2, xn. These Schrieg fibers, like all my fibers here are Schrieg. Yeah. So what I'm going to do, I'm going to apply this procedure for A being the following algebra. It's the cohomology ring of BG. And what you immediately observe is the following, that, well, I'll be writing cohomology with compact support, and that means this F lower Schrieg functor for the projection of the point. The Rand space for this particular factorization algebra obtained from this constant commutative algebra is what we've encountered before. So this is one of the easier theorems in the book of Bellingson and Drinfeld. It's kind of relatively easy calculation. Well, the thing is that one always knows how to calculate chiral homology. Well, this kind of homology, if your algebra that it started from was a symmetric algebra of something. So kind of the formation of symmetric algebra commutes with this operation. So let me just recap what I want to show. So again, want to show that cohomology of BunG with the action of Frobenius is isomorphic. Now I'll write it. Well, it's kind of intuitive statement. So you take as input your curve and BG. So what is BunG? BunG measures maps from the curve to BG. and then taking cohomology of that. And here we're taking the cohomology of BG itself, but we're taking this kind of funny integral over configuration of points. And so the Atiyah-Bott formula says this. So all right. So what the direction I'm headed in now, I want to prove it. So I want to, well, make just one more remark, well, maybe of some mathematical nature, which I can't make very precise general sense of, but I find it amusing. Well, this commutative algebra, if you see here, is naturally augmented because, well, it's cohomology of BG, and BG has a base point. Well, there is also a notion of augmented factorization algebra, augmented unital factorization algebra. So if A is such, I'll denote by A bar the non-unital factorization algebra, which is just the augmentation ideal. And it's a general theorem, again, in the book of Bellinson and Drinfeld, that if you take cohomology of the round space of A, this will be the same as just constants plus cohomology on the round space. So this procedure of going from A to A bar is something, well, it's not something very evident. So at the level of Schrieg fibers, I replace all these factors by bars. It does something, well, it's seemingly violent to your sheaf, but you can show that nonetheless at the level of global cohomology, not much changes. You just add the scalars.
When you had cohomology of BG, this is, I have to sort as living into the half category of a bond.
Yes. It's the commutative algebra object.
And intuitively, to speak of this augmentation ideal, you need a base bond, a trivial bundle.
On BG. Yes, it depends on, well, BG is pointed. So, as we said, A lives on the round space, and round space is this pre-stack, so you can't really do kind of Verdier duality on it. So nonetheless, let me just, well, put it at the blackboard. So I claim that, and indeed Verdier dual of A does not make sense. However, the Verdier dual of A bar does make sense. So let me just put it here as an object. It's another well-defined object of D of the round space, with the property that its cohomology on the round space, if I take its dual, it will be cohomology on the round space of A bar itself. Again, round space is kind of compact. So for that reason, cohomology with compact supports appears on both sides. So therefore, I'll reformulate what I want to show. So I want to go from cohomology from homology. So what I want is, again, cohomology on the round space bar, well, corrected by this missing unit. What I want is that to be the homology of BunG. So now I want to say something funny about, well, the action of the Frobenius on this cohomology. Well, the action of the Frobenius on this. well, I'm dealing with a very particular chiral algebra, and see, now for the last 15 minutes, I really was not using the fact that I'm over the ground field, which is FQ, but now let me come back to this, and I can wonder what the trace of the Frobenius on the homology. Well, what's tempting to do is to try to apply the Lefschetz formula on the round space. Well, there's no reason why it would work, so you need some convergence. So what I claim is that for this particular algebra, there is convergence, and this equals the sum over x bar, which are FQ points of the round space of, but now, well, take it in formally. These are the star fibers, because Lefschetz trace formula works with star fibers of this. But this being the Verdier dual, they are the same as duals. Well, trace the Frobenius on this. But note that the Verdier duality, this is it's the Schrieg fiber, but dualized. So let me put it as follows. So we had a string of calculations. So we started with the following. It was the product over closed points in the curve, product over the exponents of 1 minus q to the x minus e alpha. So then we interpreted this as the trace of the Frobenius on the homology, well, on the symmetric algebra, on the cohomology of the curve times this. And then we said that this is the same as the trace of the Frobenius, well, again, modulo some overall 1 on homology on the round space of this dA bar. And then I just said that this is in itself the sum over points in the round space of traces of the Frobenius on the star fibers dA. So we have the string of identities, but I claim the composition is the evident one. So this kind of Euler product is, well, just evidently the sum of points of the round space. So again, this is informal. So I did some illegal operations here, well, which needs to be justified. It's like taking star fibers, which it's a functor which is not a priori defined in our context. But the upshot is that kind of if you see an Euler product in the function field case, it is the trace of the Frobenius on the cohomology with compact support of some factorization algebra on the round space. So kind of Euler products can be interpreted in this way.
Can I ask a question?
Yes.
Classical case, if you're on S, say in the simplest case, which is 3 variables spin group.
Yes.
These things actually don't converge absolutely. That's usually the base of the proof of the computation of the Tamagawa number, say, base width. So you seem to be indicating that things converge absolutely. You don't have any base case, you don't have any induction.
Nope.
So I don't believe it converges in that case.
But
No, so the classical case of 3 variables.
well, the convergence, well,
So it's usually the value of 1.
yes, but I'll show you.
It doesn't converge absolutely.
Well,
That's all I'm saying. It's right here. If you have 3 more variables, then it converges absolutely. But the limit case, which is usually the base, that's all I'm concerned about. So you're not doing anything.
Oh, we'll do. I can show you SL2 how it does converge. For we can do
So it's not absolute.
it absolutely. We'll in function field case, we'll do P1 and
All
and SL2. But let me just finish this, and we'll do it. It'll be some geometric series over Q minus 1, and then that's we'll do the convergence.
I'm confused what is FQ part of this Hahn space. Is it a part of a symmetric power?
No, it's a finite subset. It's the union over n, and then you're taking symmetric power n, remove the diagonals, and take FQ points of that. So that's what it is.
So it's not a sum of reference parts?
No. As written in it. And again, this identity is easy identity to prove.
So what is exactly the definition of Hahn space? Because what is this S part? It's also bonds with, you look at bonds with value in some symmetric power.
No. The point of the Hahn space is just, as I said, it's a finite subset.
Subsets of Hom from S to X,
Yes.
rather than subsets of X cross S that project finitely.
Yes, it's finite subsets.
No, but what I'm saying is that family of finite subsets is not necessarily the same as finite subset in maps from S to X.
Correct.
So which one?
Again, it's a finite subset inside Hom from S to X.
What does X in Hahn mean in this sum?
Pardon?
It is under the sum F and sum. You have X in element of Hahn. What does it mean? But that was linear combination of map from FQ to the curve, if it is interpreted like that.
Just 1 second. So let me see if I'm understanding the question. I'll get confused. Let me just postpone this. Okay, let me postpone for a second, and then. Well, what I should be saying is sum over n. Take sim n of x, diagonals removed, of FQ. This is the correct thing to say. So, we just said, well, so now we're finally going to prove, well, this statement about the homology of BunG. And so here is the method. We introduce another object called the affine Grassmannian round version, which will have two projections. One that I'll call P to the round space, and the other that I'll call pi to BunG. It'll be this, and so this will be, if you wish, a principal bundle with respect to another group pre-stack, which I call rational maps from the curve to G. So let me define both objects. So Hom from S to rational maps from X to G is the following. It's a point of the round space. It's i.e. I give myself a finite subset of points of S points of the curve, and I give a map out of X times X minus the union of the graphs this point to G. So for example, if S is just, well, the field, I'm giving myself finitely many points of the curve, and I define a map from X puncture with this point punctured to G. And that's, so this is a group-like object. So similarly, we define Hom from S to the Grassmannian, just as before. It's a point of the round space. We now specify a principal G bundle. It's a G bundle on S times X and we specify a trivialization of this G bundle, again on the same set. So we trivialize our bundle on the complement to the graphs of these points. So you can easily see that, well, this group acts on this simply transitively. And the quotient is BunG. And so now I'll state kind of the actual theorem in this game. So the actual theorem is this, that the homology of the space of rational maps is trivial. So the space of rational maps is homologically contractible. So in fact, if you think of it, it has nothing, well, this space of rational maps has nothing to do with the group G. You can put an arbitrary target here. And so what you need is that Z, well, it's proved currently in a slightly weaker form than expected to hold, is smooth and can be covered Z equals to union of finitely many open subsets such that each UI is an open inside the affine space. So what I think is that what you need is Z is just smooth and rational. I don't need to actually cover it, the entire thing, by things that sit inside, each of which sits inside the AN. I need just Z to be birational to AN. So that's the actual theorem. From here, well, because, as I said, this group acts simply transitively over the fibers, as a corollary, one obtains the following, that the pi upper Schrieg functor from this category on BunG to the category on this round version of the Grassmannian is fully faithful. And as a corollary, one obtains that they have the same homology. So the traced map defines an isomorphism from the homology so the homology of BunG that we are interested in is, in fact, can be computed as the homology of the affine Grassmannian. By the way, this theorem, unlike the Atiyah-Bott formula, holds for any G. It doesn't have to be, well, any meaning any. Not simply connected, not even reductive, not semi-simple. So true for any G.
But you don't need this decomposition to pieces in affine space.
Oh, it's G. It's a connected affine algebraic group. Bruhat.
No, but if it is split, but if it is non-split doors, what will you do?
Oh, it's a geometric theorem. So again, I'm doing this. So
And you don't even need
connected, of course, because otherwise the space will be disconnected. Okay, so now, last step that I want to perform is to see how this implies what I need about well, the actual Atiyah-Bott formula. So what we notice is that, well, as we said, this affine Grassmannian is endowed with a forgetful map to the round space, and it factorizes with respect to this projection in the same sense as in the definition of factorization algebra. So therefore, if you do p lower shriek of this dualizing sheaf on the run space and call it B, this is a factorization algebra. So if you wish, the shriek fibers of this are the homologies of the affine Grassmannians. And so it's also augmented by virtue, homology, well, it's augmented by means of the projection to the point. And so first of all, we have the cohomology, homology of the affine Grassmannian, which is by definition cohomology with compact supports on the affine Grassmannian with coefficients in omega. The dualizing by this is the same thing as cohomology with compact supports on the run space of this B, in which, as was said before, it's the same as cohomology of the run space of this augmentation ideal plus constants. And if you compare what I need and what I have, so I combine this isomorphism with this isomorphism, and so remains to show the following, that cohomology of compact supports on the affine Grassmannian of this D A bar is the same as cohomology with compact supports on the run space of what I call B. But here comes this next theorem, which says that D of A bar is actually isomorphic to this B. And so this is, well, this is known in topology as E2 Koszul duality. It tells you how homology of the affine Grassmannian is related to the cohomology of the classifying space BG. But it's, well, in topology, the expression is that, for this is that the affine Grassmannian is the double loop space of BG. But this situation is explicit enough that you can actually prove it within algebraic geometry. This is a local calculation which amounts to what we wanted to prove initially, namely the Atiyah-Bott formula, but in the simple case of P1, and then you can just do it. So again, so here is the string of isomorphisms. This implies this, which, well, if you combine these isomorphisms, we arrive to what we wanted to get, which is the Atiyah-Bott formula. So that's it.